Hello everyone, my name is Emiliano Larach and today I'm going to be going over lab number 5, which deals with Faraday's law and breaking of magnetic braking. So the purpose of this lab is to experiment with a bar magnet falling through an aluminum tube in order to observe and apply Faraday's law. In here you can see the magnet going through, generating a change in magnetic flux, thus creating an EMF. Some important formulas that we're going to use are Faraday's law, Biot-Savart law, Ohm's law, magnetic force on a loop, and Newton's second law, as well as Newton's third law. Going through quickly over our results, we have that our computational time was 1.57 seconds for the magnet to fall completely through the tube, and the experimental time of 1.24 seconds. Our model is simplified. Our magnet was used to represent a magnetic dipole, and the aluminum foil was a tube through which it fell. And we consider this tube as multiple rings stacked upon each other. Some assumptions that we made for this lab are that gravity and the magnetic force from the tube are the only forces experienced by the magnet, and that air resistance is negligible. For our experience, our system is the aluminum tube and magnet, our surroundings is everything else, and how I did this was, having identified the north pole of the magnet with my phone, I proceeded to drop the magnet through the tube 5 times and recorded how much time it took to fall through the tube, for then averaging these times to get the result that I mentioned earlier of 1.25 seconds. Why can we use ferrous tube, for example, steel pipe? So steel pipe is a very magnetic, it induces a very high magnetic, a very high resistance in magnetic flux. So the magnet will just stick to one of the sides of the tube and it will not fall through, and we will not be able to do our experiment. Then what happens to the magnet? How does it compare to a magnet falling in free space without a tube? So without a tube, it would fall quicker because we don't have this opposition in magnetic flux being generated by the conductor rho. For our Ghost script code, first we initialize some variables and important parameters from our aluminum foil roll. Then we create the bar magnet in GlowScript and created the aluminum foil roll. And these two very important equations that deal with calculating the magnetic field from the dipole and also the change in magnetic flux. Then we calculated the two forces that we are considering, so the gravitational force and the magnetic force. For the magnetic force, we calculated the force on the magnet due to the tube and on the tube due to the magnet. And then for having the net force, we just added these two forces. Obviously, the magnetic force will go upward because it's resisting the movement, and the gravitational force will go downwards. In here, we can see our code, how it runs, and we can see this very particular shape that we are going to discuss later. So we know that the red current is going counterclockwise and the blue current is going clockwise, and we know this because of Lenz's law and using right hand rule too. So when we flip the magnet around, so if the south pole was pointing upwards, the magnet would take the same exact time to fall through. It's just that our current directions would be flipped. And also the shape of the graph of velocity versus time. So we can see here about the forces. It tells us that in here we only have the gravitational force acting on it, so it's falling very fast. Then it reaches, when it enters, you have the two forces counteracting each other, so it reaches terminal velocity, and then when it goes out, it starts to fall quickly again. So some possible errors are not accounting the time the magnet takes to fall accurately, some currents of air that could exert some forces, and the thickness of the aluminum foil not being measured accurately. So what if the resistivity of the conductor were thus as close as possible to zero? How would the dynamics of the falling magnet change? So the magnet would fall slower through the tube if our resistivity was zero. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So to account for this, the magnet would fall quicker because you have less material, and to account for this in our model, we would either need to reduce the height of our tube or reduce the radius. So as a conclusion for our lab, this lab allowed us to better understand Faraday's law and how a change in magnetic flux can cause an EMF. And also we were able to observe and calculate the relationship between EMF and forces, magnetic and gravitational. We have done some of these problems in our class, and it was good to finally be able to apply them in the real life. That is all for my video. I hope you enjoyed it, and if you have any questions, please let me know. And also please take a look at my glow script code that you can find in the description. Thanks.